Hello, my name is Sean Wood and I'm the sales manager here at Clearview Imaging. Today I'd like to talk a little bit about camera sensor comparisons and why sensor performance is an important consideration when looking at selecting the camera for your next vision application. I will specifically be looking at the comparison of a range of 5 megapixel sensors which are available in different camera models from Point Grey. When selecting the camera for a vision project, there are of course the basic factors to consider, like resolution, frame rate, interface and sensor size. You may also consider the implications of using a global shutter versus a rolling shutter, but this isn't always enough to choose the best camera for a specific application. This is where it's helpful to understand the imaging performance of the sensor itself. Traditionally, this has been a fairly difficult process as there was no set criteria for camera manufacturers to test and report against. The introduction of the EMVA 1288 testing and reporting standard for machine vision cameras has provided a level playing field when it comes to the testing and reporting of imaging performance from one camera manufacturer to another. The standard ensures that all manufacturers who subscribe to it test their cameras in the same way and report their data against the standard set of measures. Point Grey were one of the first manufacturers to test all of their USB 3 and GigE cameras against this standard, and they provide all of the data in an imaging performance document for each of the cameras within a specific model group. We will use this data to form the basis of our sensor comparison. The 5 megapixel sensors that we are testing include a range of both CMOS and CCD sensors, and as we progress it will become apparent how far CMOS technology has developed in comparison to CCD, which was always traditionally viewed as a superior technology. The sensors we will look at today are the Aptina 5 megapixel 1/2.5 inch CMOS, the Sharp 5 megapixel 2/3 inch CCD, the Sony ICX655 2/3 inch CCD, the Sony ICX625 2/3 inch CCD, and the new Sony Prodigy IMX250 2/3 inch CMOS sensor. The first measure we will look at is quantum efficiency, or QE. Put very simply, this is the efficiency of the sensor in converting photons, or light, to electrons. The EMVA 1288 standard dictates that the QE score is reported as a percentage at 525 nanometers, which is the wavelength of visible light. This is also shown as a graph, as it's useful to understand the sensitivity of the sensor at different wavelengths. Near infrared, for example, if this is the dominant light source for your application. So here, the red dotted line marks a 525 nanometer or visible wavelength, and this is where the QE % score is taken from. Based on this, the Sony Prodigy CMOS sensor in the Grasshopper 3 range is the best performer at 525 nanometers, and indeed across the rest of the reported spectrum into near infrared. Here, reported as a QE score, you can see that the Sony Prodigy IMX250 sensor converts 70% of the photons to electrons at the visible wavelength, compared to the least sensitive sensor in this test, the Sharp 5 megapixel CCD, which converts 57%. QE is an important factor to consider for low light, high speed applications, where you want to use a short shutter time as possible to gather the information or light that you need to conduct your image analysis. Next, we will have a look at temporal dark noise. Temporal dark noise, again very simply, refers to the noise present in the sensor before any signal or light is present. It is measured and reported in electrons. The amount of temporal dark noise is directly attributed to sensor design. This differs to shot noise, which is a fixed and natural phenomenon and is always equivalent to the square root of the number of photons generated by the light source. Let's see how the 5 megapixel sensors compare here. With temporal dark noise, the lower the score the better. This is because the dynamic range of the sensor, which we'll move on to in a minute, is determined by the ratio of noise, temporal dark noise, versus the signal. If two sensors receive the same signal, the sensor with the lower temporal dark noise will have a higher dynamic range. You can see here again that the Sony Prodigy IMX250 CMOS sensor comes out on top, with the Sony ICX655 CCD being the noisiest of the sensors tested. Before electrons are digitized, they are stored within the pixel, referred to as the well. The number of electrons that can be stored within the well is called saturation capacity, or well depth. If the well receives more electrons than the saturation capacity, the additional electrons will not be stored. Here, the Sony IMX250 CMOS sensor has the highest saturation capacity, whilst the Sony ICX655 CCD has the lowest. Saturation capacity is important for maximum signal to noise ratio and dynamic range, as this is the maximum signal or the maximum number of electrons that can be collected. We will look at both the signal to noise and dynamic range as we progress. When evaluating camera performance, it is very common to refer to signal to noise ratio and dynamic range. These two measures of camera performance consider the ratio of noise observed by the camera versus the signal. The difference is that dynamic range considers only the temporal dark noise, while signal to noise ratio includes the shot noise as well. The signal to noise ratio is measured and reported in decibels or dB, and sometimes in bits. Again, the Sony IMX250 CMOS sensor is the highest scoring of our 5 megapixel sensors, with the Sony ICX655 having the lowest signal to noise ratio. A high signal to noise ratio is invaluable in low light imaging applications for which every available photon may be significant. As mentioned previously, the dynamic range of a sensor is a ratio between the signal and the temporal dark noise. It is also measured and reported in decibels or bits. Here, the results are shown in decibels. By now, I'm sure you won't be surprised to see that the Sony IMX250 CMOS sensor is top of the class again, with the Sony ICX655 finishing in last place. The dynamic range of a sensor is a crucial consideration when you need to capture information in both bright and dark areas of an image. Applications where cameras are used outdoors in bright sunlight and dark cloud would be a good example, as well as industrial applications like welding inspection where you need to observe both the arc and the weld seam. The absolute sensitivity threshold of a sensor is the number of photons needed to have signal equal to the noise. This is an important metric because it represents a theoretical minimum amount of light needed to observe any meaningful signal at all. Absolute sensitivity is measured and reported in photons, and the detail of how this figure is reached is complex and best left for another day. Again, for this metric, the lower the reading the better, as theoretically this means you need less light or signal before you can acquire meaningful information from the generated image. The Sony IMX250 leads the way here also. This is not surprising, as absolute sensitivity is determined by considering a number of the other metrics covered, where the Sony CMOS sensor outperforms the other options in this lineup. Frame rate is not an imaging performance metric like the others that we have discussed, but it is an important consideration for your application. It's not always determined by the sensor itself, and the interface used to get the data from the camera to the PC may be the limiting factor. I've included it here because it's often the first consideration when thinking about specific applications, particularly where you only have a brief window of time to image a fast-moving subject. It's with high-speed applications like this where it's really important to look at the other performance metrics that we have covered. If you only have a very brief window to capture signal, you need to ensure that the sensor has the sensitivity required to capture as much of the available signal as possible, and that as much of this captured signal is usable to provide meaningful information. The Grasshopper 3 over USB 3 using the Sony IMX250 sensor generates 75 frames per second at full resolution. This, combined with the outstanding performance from the other metrics that we have covered and a global shutter, make this option the clear winner for the high-speed low-light application. Another key factor to consider is cost. If one of the other sensors here provides the performance that you need for your application but costs less than the IMX250, then this is the key consideration. For example, the Aptina CMOS sensor in the Blackfly GIGI PoE range offers good performance across the board, but is by far the most cost-effective option of this lineup. If the performance is adequate for your application, then it will make no sense to overlook this option. What we have seen today is that 5 sensors with very similar headline specifications can vary greatly in performance. We've also seen how important it is to understand the imaging performance of a sensor in relation to its specific application. Traditionally, it has been very difficult to carry out this kind of comparison due to the different ways in which manufacturers reported this imaging data. EMVA 1288 has made a real difference here, with camera manufacturers like Point Grey testing to this standard and providing their test data in a clear and uniform way. It has made carrying out this essential comparison of options much more straightforward. It's always advisable to test the actual camera itself for your specific application, but this type of data and comparison makes it easier to narrow down the options for testing. We've also seen that the IMX250 sensor, which is one of the latest models in the groundbreaking Sony Priatus range, has clearly positioned these global shutter CMOS sensors at the front of the pack when it comes to imaging performance. CMOS sensors are now a genuine alternative to CCDs for many applications. I hope you have found this comparison useful, and please do contact me via our Contact Us page if you need any more information. Thanks for watching. Goodbye.